silent me. Good morning. Here we come, joining the classroom and getting ready to go, getting our technology up. Good morning, and live from Santa Barbara, Winter Hall 110. This is Mayterm, CS-030. This is our last lecture class today. And we are part of a 5-week seminar class. That was kids booing. We can't hear the booing kids. This is part of a 5-week class that we're wrapping up today, for lecture anyway. Today's lecture is scheduled for 2 hours, and we're communicating in real time on Slack for those who have access to our Slack channel at #broadcastquestions. Hope everything is going well for the folks remotely still, having a little bit of touch base every now and then with you guys, and of course our local people here as well. Hope things are going well with you too. Where are we at? Well, let's just arrive for the day. Make sure we're here. Have our notifications and cell phones ready to go. What is everyone grateful for? Grateful that you transferred here. Is this your first full year? Yes. And what year did you transfer as? Grateful that you're here. Joy. Grateful for surviving Mayterm. It's a good one. I would say that there's a low level in which I'm grateful for coffee. I'm very grateful for coffee very often. I'm also grateful for this conference that's going on and the chance to talk at it, because things like that force me a little bit to think through stuff that's sort of bubbling around in my head and don't really ever sit down and actually work it out. So just nice to have a forum that's reasonably friendly and but intellectually stimulating and challenging. I guess what you're describing your parents who were at the conference enjoyed too. Great. Okay, so just administratively, today we have a quiz on Chapter 17 due this evening. We have a final tomorrow. And the final, if you're taking it in person, will be proctored by Dr. Hunter, and he will join the in-person folks down here. If it's being proctored, if you've got an arrangement to proctor somewhere else, that's set up already. And then if you are remote, you'll be taking it through Proctor Free, and that also should be all set up and ready to go. There's a 10-hour window that's available to take it, starting at the same time that our in-person folks are taking it, which is 10:15 a.m., with the mysterious, unexplained impact of time zones on how Canvas releases stuff. I'm sure I could find the answer to that out if I tried, but I haven't looked very deeply. And then I will be spending the weekend and early next week catching up on all the grading. So if you are around, please keep connected to email and Canvas notifications in case I run into any glitches with any of your assignments. There's always something, just regularly people turn in the wrong file or something happens. And so I might need to be in touch with you in order to make sure that I can resolve that before the grades get submitted to the registrar. Anything administratively we need to cover before? How is the drone going? How did the drone go? Pretty good. I know remote. We got a remote question about whether or not it's possible to be able to tell how far apart two people are, and whether it's possible to set up a map to do that. And it definitely is. All the places in the drone simulators have a latitude and longitude associated with them. And there's a class in the simulator called, I think it's distance utilities, and distance utilities will tell you the distance between two latitude and longitude points. So the way you get to it is you have to figure out where you find a person somehow, they're in line or wherever they are, and then you find the place where they are, and then you find the latitude and longitude of that place, and then you look at where the person wants to go, that's a place, you find out the latitude and longitude of that place, You put latitude and longitude of place 1, latitude and longitude of place 2 into the distance calculator, and that'll give the distance between where they are and where they want to go. But keeping track of all those distances, that requires you to set up some sort of a data structure if you wanted to do something elaborate. There's an algorithm called Dijkstra's algorithm that we don't have time in this class to get into, but we've been talking about data structures like linked lists and sets, and today we're going to continue talking about trees. The next progression in data structures, what you would talk about or what you'll talk about in another class following on from this, if you continue, is a data structure called a graph. And a graph is kind of like a friend network on Facebook. If you imagine that each person is a node and the connections between them, the links are friends. So it's like a tree, but the links coming out of a tree can go back up to a higher point in the tree. And so all the nodes can connect to all the other nodes, and you can have paths through the trees that are circles and different structures like that. So I guess another way to think of it would be what it would be like if you had a map where cities were nodes and the roads were edges, and you don't just have a tree that goes down, but you actually have connections between all of them. So that would be a graph, and a graph would be a natural way to set up distance calculations on the map, because you would draw lines between all the different locations and say, how long are they? So you put a label on the edge. And that takes a little bit more preparation in order to understand it, but if it's something you're interested in, there's lots of resources online for looking up Dijkstra's algorithm. And that is DJI, Dijkstra. I think it's Dutch. All right, so last time, what we were looking at is trees. We were talking about our second set of trees. And one of the things that we studied is we looked at tree traversal, being able to know how to get through a tree using pre, in, and post-order traversal through that tree. The difference between them is the order in which you do your recursion. So if you're at a particular node and you're doing a pre-order traversal, you process the node you're at before you process the left side and the right side. If you're doing in-order traversal, you first recurse on your left side, complete everything on your left side, then you process yourself, and then you process the right side. If you're doing post-order traversal, you first process the left side, then you process the right side, and then you process yourself, kind of as you're coming back out of the recursion. We studied that in the context of balanced trees and the properties that balanced trees have. And the thing that we like about balanced trees is that they have these nice formulas that you can use for heights and nodes. And so one of them is up there. That one at the top is how we calculate how many nodes are in a tree. And that's going to be equal to 2 to the power of h, where h is the height of the tree, minus 1. So if the height of our tree is 2, then we have 3 nodes in our tree. And that assumes that our tree is completely filled out. So that's the height of a completely filled out binary tree. We'll have n nodes in it. You can do the reverse calculation by solving for h, in which case h becomes the log base 2 of n minus 1. And then the height of the tree is going to be, you can calculate the height of the tree by calculating the log of the number of nodes in the tree. The only thing you have to be careful of is if you don't have a completely filled out tree, the value that you get for height is going to be fractional. So you get 3.8. And so in order to fill out a tree where you need 3.8 levels in your tree, well, you're going to have to round up to 4 to make sure you get everything that needs to be captured in that. After we looked at the tree traversal, just how that works in general in recursion, we looked at how we could implement the visitor pattern, where a traversal through the tree could be done independently of the kind of work that you thought needed to be done at each node. So one obvious thing that you can do is you can just print out what's the data you can print out the data at each node in your tree, following the different pre, in, and post-order traversals. And so we did that first, and we did that by just hard coding the work of printing out the data at each one of the nodes. And then we said, well, instead of printing out the data, why don't we just pass the data to a class? And that class can do whatever work it wants to do on it. We'll allow users of our tree structure to give us that visitor class, and then we'll just allow the visitor class to process the data as it goes through. And in that way, we're able to separate out, we're able to make independent the idea of moving through the tree with the work that's done at each element of the tree. And we want to separate those out because as someone who's implementing the tree, we want to be responsible for traversing through the tree. But the user of our tree wants to be able to declare what work they want to do at each node. Summing the elements of the tree, finding a particular element in the tree, aggregating all the elements in the tree through a sum, or maybe putting all the strings together. What else might you do in a tree? Replacing something in the tree, maybe modifying all the elements in the tree. Those are all things that you might want to do. So we looked at algorithms to determine the size and the height of a tree. We showed size and height in just recursive manner. To calculate the size of our tree, we took 1 and added it to the size of our left node and our right node. To figure out the height of our tree, we took 1 and we added it to the highest height of our left or our right node. So very similar algorithms. And then we implemented the size algorithm using the visitor pattern by sending a visitor class around our tree and having the visitor having an instance variable which kept track of the number of nodes it had visited so far. And then finally, we introduced binary search trees, and that's what we're going to pick up today. This tree that is on the screen right here behind me, perhaps my head is covering it. Let's see if we can fix that. That tree is not a binary search. It's not a binary Seath tree either. Seath is a Star Wars character. Let's fix that before we go ahead and call it a search tree, not a search tree. Why? So why isn't that a binary search tree? What is it about that tree that violates the binary search tree property? And let me just remind you that the binary search tree property is this one. This is kind of abstract and maybe not the best graphic in the world, but what it says is it says that for any node x, the children on the left side will be less than x. The children on the right will be greater than x. So we come back here. What makes this not a binary search tree? Right. So with A being in the middle, everything to the left has to be less than A, and you see immediately that B is to the left, and that's violating. Now the tree has some structure otherwise, and so that's why it could possibly be a little confusing if you don't understand clearly what a binary search tree is, because it's very clearly going A, B, C, D, E, F, G, H, I, J, K, L, M, N, O by reading across, right? So there is structure there, but the structure is not what you need for a binary search tree. Just to remind ourselves about that, we have this idea of a tree, we have a binary tree, and then we have a binary search tree. And what changes when you go from a binary tree to a binary search tree is the binary search tree has rules about the contents of the tree. And so binary trees, you don't care what's in them, but binary search trees, the contents matter. And so in order to make sure that your binary search tree works, you have to implement comparable. Whatever you're storing in it has to implement comparable, because you have to be able to tell when you're building that tree whether something should be on the left side or the right side. Okay, so to practice working with this, let's start by doing a little exercise. And what I would like you to do is either on paper or with some sketching software, whatever you've got available to you, try and take this partially filled out binary search tree that contains integers and try and complete it in such a way that the binary search tree property is maintained. Okay, so fill in the empty boxes so that it is still a binary search tree, and you leave the 2 and the 5 and the 23 where they are. Okay, so let's take 5 minutes to do that, see how that goes, and then we'll come back on. Yeah, you can do it on the board. Okay, we did it here on the whiteboard. That's a benefit of being in class, and worked in teams. And we were able to come up with a solution, and I think it was pretty good because it enabled us to think through exactly what's going on in a binary search tree a little bit. Now, my solution looks like this. And how did we match with what happened in class? The left side is pretty constrained because you can't fit many more numbers between as long as you're keeping it non-negative. So I think we probably matched exactly on the left side. And then on the right side, there was more flexibility, and looks like a little different because there was more space to add numbers in between. As we went through and checked, one of the things that I pointed out here in class was that as you're looking at a particular node, for example, 3, the highest value on the left side entails going down 1 and all the way to the right. So 2 is the highest element on the left side. And we know that the highest element on the left side has to be less than 3. Likewise, the lowest element on the right side is going down to the right and then all the way to the left, so the 4. So we know that 2, 3, 4 maps the binary search tree requirement. And so that half of the tree is good. And then we can go all the way to the root and do the same thing. Well, 7, we go left 1 and then all the way to the right, we get 6. So that's good, 6 and 7. And then if we go to the right and all the way down to the left, we get 8. So 6, 7, 8 is good pattern for my tree. So we had that same effect in the tree in class. So good. That's the basic idea of a binary search tree and how you can fill it out. Now, one of the things that we looked at last class, and we won't go through it again, but we noted that when you draw a binary search tree or when you add things to a binary search tree, if you start with an empty tree and you add them in order, you get different shaped trees. So we took Lisa's name last time and we considered adding the individual letters in her name to a tree. And we saw that if we added them in order, L-I-S-A, and built out the search tree like that, we ended up with a tree that had, I think, 3 elements to the left of the root. But if we did it backwards and we started with A, because A is going to be the first, if you start with A, everything is going to have to be to the right tree. And so a binary search tree is not unique. The shape of that tree depends on the order in which you add those characters. And so there would be a particular ordering in the tree that we just looked at that would enable us to get that tree. But unless we added things in the correct order, we wouldn't end up with that tree at the end of the day. The data in the tree, like I said, must be comparable because we have to be able to decide whether a node should be to the left or the right. We can only do that if we can compare 2 of the data types that are being stored in the tree. So exactly what do we do when we add things to a binary search tree? What is the algorithm that we follow? When we were doing that exercise a moment ago, we weren't really adding things to a tree. We were kind of solving a puzzle. It was almost like a Sudoku-style puzzle for a tree-shaped structure. But when you actually are working with a tree and you're adding things to the tree, it's typically in the context of a program. It's going to be iterative, and so you're going to add things to the tree one at a time. So an algorithm for inserting the data into the tree might look something like this. We want to insert something into the tree. And it's recursive. So if we encounter a non-null node reference, meaning we're at a node in a tree that has data, we want to look at the data. And if the data value of the node we're at is larger than the value we want to insert, then we're going to recurse down the left tree. And we'll say, we'll take this data and insert it somewhere down my left tree and just recurse on it. But if the node's data value is smaller than the data that we want to add, then we're going to add it to the right tree. We'll just recurse on the right tree. If the node's data value is the same as the one you want to insert, well, basically you're done. It depends exactly what you're doing. But if you're using the tree to keep track of a set and you only need one element of everything in your tree, then you see it's already in the tree and you can just stop. That's if you're using a set. And the reason why the assumption is that you're making a set is because this tree data structure is what underlies a tree set, which we've seen already. We've used the tree set as just an applications programmer, but this is how a tree set is implemented. Finally, if we encounter a null node reference, for example, there's nothing in our tree and we start at the root, or we have followed our tree down left and right paths until the point at which we get to a null node, then we're just going to put the new data at the end of our tree, either on the left or right side, whatever is appropriate given the current node's data value. So what does that look like? Well, if we did a sequence of adds and we added names, starting with some kind of a binary search tree, adding things in order dictates the shape that we get. So in this case, what we're doing is we're starting by adding Juliet, step 1 there, and that causes Juliet to end up at the root node. That then dictates a partitioning. That means that our tree is now going to be split on the letter J, and everything to the left is going to be alphabetically before the letter J, or more specifically, alphabetically before Juliet, and everything to the right is going to be alphabetically afterwards. So we're partitioning our data based on the first thing that we entered. The second element that we entered was Tom, and Tom has to respect the partitioning that we've already established. So Juliet already set the stage for what we're going to do for the rest of our tree, and so Tom has to be put down on the right side. Clearly, that would have been different if we had started with Tom. If we had started with Tom, our data would have been partitioned around the T. But we didn't. We started with Juliet, so that's how our shape proceeds. Then we add Diana, and we consider, well, is Diana alphabetically before Juliet? She is. And the left node at this point is null, so we're going to add Diana hanging off the left side. And finally, we add Harry, and Harry is less than Juliet, so we go left. And now we imagine we're just inserting Harry into a subtree that's rooted at Diana. Everything to the left of Juliet is partitioned around Diana. Harry is greater than Diana. So we add Harry to the right side of our node. We end up with a tree. So the sequential calls to the tree's add method are what's generating the data structure. This code represents what an application programmer would be writing. And you can see that from the perspective of an application programmer who's working with this tree variable, this reference to the tree, they're assuming that a contract is present about running a binary search tree. But there's nothing about what's happening here that is revealing what's happening inside the tree. The application programmer is just believing that these things are being added correctly, and it's up to the systems programmer who's implementing the binary search tree to make sure that it's being done correctly. So there's a pretty clear separation of responsibilities about whether you're using this abstraction or whether you're building the abstraction. This is a using abstraction situation. All right, so suddenly we add Romeo. Romeo, we would like Romeo to be next to Juliet, but alas, Juliet's children are already formed. So Romeo, we have to pass down the tree, and we say, Romeo, Romeo, wherefore art thou, Romeo? Oh, wow, that was like a setup. That was awesome. Greater than Juliet, at least alphabetically. And so we're going to pass Romeo down to this node and say Romeo and Tom. How do we feel about that? Well, RST, so Romeo is less than Tom alphabetically, and so we proceed and add Romeo as the left child of Tom. The binary search tree property is maintained. Romeo has been added to our tree, but alas, Romeo and Juliet are separated by the third wheel, Tom. All right, so here's some code that looks at the process of what it would be like to add a node to the tree. And rather than editing it, I just grabbed a screenshot here so that we could look through it together. So for starters, recall this is an interior class that's present within our binary search tree. And that when we built it out, we wanted to make sure that whatever we stored in it extends comparable. Because we want to make sure that we want to make sure that eventually we're going to be able to call compare on the T node right here. We need to make sure this is a method that's available, and the only way to make sure that this method is available in our data is to restrict the data that we can store to be those classes that implement comparable. That's why that's there, is to create a compiler verifiable connection between this method that we want and what we're allowing our application programmers to put into our generic slot. Every given node keeps track of some data for the user. The data is going to be of type T. When we declare it, we don't have to describe how it's constrained. The constraints are only present when we declare T as a generic class. When we use it, we just say T. And then we know that we have something to the left and to the right, and those two things are references. They're references to something of the node class, and whenever we declare an instance variable of the type node, we also have to specify what its generic type is. We don't have to be concrete about this because we're within the we're doing the systems programming. So whatever it is that we have been whatever it is we've been instantiated with, that's kind of the wrong word. Whatever type we've been defined or constrained with, we want to make sure that our children on the left and right have the same constraints. Now when we add our node, like we did when we added Romeo, we're going to get some new node passed in. And the first thing that we have to decide is we have to decide whether or not we should be passing Romeo to the left or to the right. So to do that, we look at the node that we currently contain, or sorry, we look at the data that the node that's coming in contains, and we compare it to our data here. So our data corresponds to this data right there. This data variable corresponds to this data variable here, because we're not calling it with a dot notation. The dot notation means we're looking inside new node to find new node's data. We compare data. We compare data here. Oh, that's an ugly drawing, sorry. Compare data with the other data. And we decide whether or not the node that we're adding should come before or after our current data. If it should come before, then we know that comparable is going to end up being less than 0, or COMP here is going to be less than 0. That's what compare to does. It decides whether the variable on the left should come before the method variable. If the one on the left should come first, then compare is going to evaluate the negative number. This method will yield a negative number, and we are capturing it here. We're then checking it, and we see that, oh, it should go down the left side. So as long as the left side is not null, we just recursively call the same function starting with the left node, as if the left node was the root. But if we don't have a left node, if there's nowhere to go, then we're just going to add the left. We're going to put this new node on the left side. So this is like when we're at Tom, we're just going to put Romeo on the left node of Tom. If comparable is greater than 0, then it means that data should come this new node data should come after data, meaning it should be on the right child. And so we end up in this bracket here. And if right equals null, then we're done. We just have this new data hang off the right side. But if there's already data on the right side, because right is not equal to null, then we just recursively add it to the right side. And the recursion does the work for us. This is a great example of when recursion is really powerful. It's really a good time to use recursion, because you're able to think about it in terms of a smaller problem and an ending case. The smaller problem is adding it to one of your subtrees. The ending case is when your subtree is null. Good setup for that. Thoughts on adding things to a binary tree? Can you guys imagine some sort of world in which you had a tree that was a tertiary tree? So a tree that very explicitly had a left, center, and right child instead? It's computers, we could do that if we wanted to. How would you arrange that tree if you wanted to do something like a binary search tree? Yeah, it's not really clear, right? The binary search tree has a really nice mapping to less than or greater than. So maybe what you could do is you could have the center node be all things that are equal to the one above it. But that, I don't know if that's super valuable, because then you have your root node and everything down the center line would always be equal to the root. I mean, maybe there's some kind of a world in which you want to split things in multiple directions. Like, rather than just having left and right, what if you had left, right, up, and down? So you had a four-way tree maybe, and what you were keeping track of at each node was a two-dimensional point, like maybe a point, like a latitude and longitude point. And then what each one of your branches would be, would be something like, is it to the north, is it to the east, is it to the south, or is it to the west? And then you could use a four-way tree to do something like that. You could partition your points into a geographic search tree. And then if you think about that, you could do it in 3 dimensions, where what if you had cubes, and you had each point was a 3-dimensional spot, and then you had 8 children, and that represents each of the different quadrants around a center point. It could be like up and north, up and east, up and west, up and south, down and north, down and south, down and west. Split things like that. So there are some data structures that take this idea of a binary search tree and extend it to different kind of mathematical worlds. The geographic one is called a KD tree, and it alternately splits between different it's a little more complicated than just splitting around north, south, east, west, but it kind of takes that structure. And so in geographic information systems, GIS systems, that's often the native way in which things are kept track of. It's in a tree, but a tree that's extended to support latitudes and longitudes. So as we think about binary trees, it's important on the one hand to understand, the low-level structure of the tree, but it's also kind of important to understand what it is we're doing with the tree and how we're creating these properties of a tree that we could leverage in other circumstances for different kinds of data. And because we're programming this, we have the flexibility of creating other kinds of data structures as well, if we find that something would be more useful. Okay, well, we know what to do when we're adding something. Removing something from such a tree is a little bit trickier. There are basically 3 different cases we want to consider when we're removing something from the tree. The first case is when there are no children. So this is the image on the upper right. What we have is we have a binary search tree and one node labeled parent, and the node that we want to have removed is the one that's in the lighter pink and also labeled node. If that's the one that we want to remove, it is fine to just cut that link and set parent.write equal to null. Because if we do that, the binary search tree property will still be maintained. That's the main thing that we're concerned about. As we remove the nodes, we want to make sure that we haven't broken any of the binary search tree properties. And if we cut that one off in the bottom right, I think we're in pretty good shape. We just removed one single node. There's no children on it. We're okay. So the second case then is what happens if you want to remove a node that has one child? Well, we know we want to remove it. What do we do with the link that comes from our parent? So the link that comes from our parent here has to be cut because we're removing this node, but there's a bunch of data down here that we don't want to have removed. We're just removing one node. We're not removing a whole subtree. And so this data has to be saved. And so what we're going to have to do is we're going to have to say something like parent.write equals remove.left. And then that's going to take this link here and redirect it where this dotted blue link is along the way. And then anything that's hanging off this tree is still going to be there. And we said that this node only has one child, so there's nothing over here. And so if we think about that, we can be pretty confident that the binary search tree property is still being maintained, because we know that when we started, everything to the right was greater than the parent. And when we remove this node and we connect this link to here, well, this was already to the right. So if it was already to the right and we had a tree that had already had the binary search tree property, when we move the child of the node to be removed to the right of the parent, well, the property is still maintained. So we're okay. The third case gets a little trickier. The third case is what happens when the node that you want to remove has 2 children. So the node that we want to remove in this case is here. And the reason why this is tricky is because the parent node is going to have to be changed because we want to remove this. But it's not obvious what we want to connect this node to, this link to. If we connect it here, we're going to lose this entire subtree. And if we connect it here, we're going to lose this entire subtree. So we have to do something so that we have this position in the tree still there, but we need our binary search tree property to be maintained. So what we can do is we can replace this slot with the smallest element from the right side of the tree. The smallest element from the right side of the tree is going to be what happens when we go right 1 and left as far as we can go. So if we find this element, then we recursively ask to remove this element from the subtree. So again, the recursion is important. So the first thing then we have to tackle is trying to remove this node. The original question was to remove this one, but that bubbled down the tree so that we had to remove this node. Well, removing this one's okay. It's not hard to remove this one because it only has one child. And when we want to remove one child, well, we just take the parent link and we redirect it to the child link. And that means that everything that was to the left of this node here and was less than the value of this node is still going to be less than, because this has now been moved up and it's less than. This node had no right length, so there's no problem there. This node had no left length, so there's no problem there. Now, we didn't want to delete this data permanently. We just wanted to remove it from this subtree, because we want to take this data and now we want to replace the data that we were going to remove with that bit. The reason why this is nice, or why it's required, is because this is the node that has to be put in here to maintain the binary search tree property. We know that this element is the smallest element of the right tree. So there's nothing higher than it, or there's nothing less than it in the right tree. So if we move this up here, everything that remains is going to be greater than this element. But we know that it started on the right side of the tree, so it also has to be greater than everything to the left side. And so as we bring this element up, we're confident that the binary search tree property has been maintained. But it's required us to make a recursive, first find the lowest element, and then recursively remove this element before we're done responding. There's one other way that we could have tackled this. The way that I've described it is I've said that we're going to go find the smallest element from the right side of the tree. Well, what's another way we could have tackled it? We have a binary search tree. We said that one thing we could do is we could take the smallest element from the right subtree. That would have maintained our partition. What would be a parallel thing we could do from the left subtree? The largest from the left, right? So whatever we replace here, we just have to make sure that all the children are partitioned well. So we could take the smallest from the right, or we could have taken the largest from the left. Either one of those would have been an appropriate choice to put in. That made me think of something which then promptly left my brain. Both of those solutions would have required the same recursion. And in this case, it would have been simpler because the largest from the left side is simply this node. So we could have simply moved that into there without having to do a lot of work. Yeah, okay. Whatever it was I was going to say, I forgot. We'll move on. Okay. Here's an interesting fact about binary search trees. If you traverse a binary search tree using an in-order pattern, what you get back is a sorted list of all the elements in your tree. What? Binary search tree, regardless of the shape, if you do an in-order traversal, is going to yield a sorted list as a result. Let's just do a traversal on here in order. So in order means we do left, center, and then right. And so we're going to come down here starting at 7, 3, 0, 1, 0. So first we're going to hit 0. Then we do the node we're at 1. Then we do 2, 0, 1, 2. Then we come back up and do 3. Then we handle the right side, go right, and then left before we handle center. 4, 5, 6, 7. Now we go right, but we don't process that one yet because we're doing in order. So we go left. We don't process that one yet because we're doing in order. Then we do 8, come back, 13, 23, come back, 24. Move down here, but don't process it yet. Move left, 25, 27, 29. So an in. You mean, because of the way it's drawn, it's like having a fence here that slowly goes across there, drawing one thing at a time? Uh-huh. Right, yeah, so Yeah, so I guess for me, if I had a line that was kind of like that across it. Yeah, a well-drawn tree. A well-drawn tree has sort of a sense where you're dragging this line across it to do it in order traversal. Well, no, I mean that kind of observation is important, maybe not for the moment, but it's the kind of thing that you remember and later on might become important for some other thing that you end up doing. And those are the kinds of connections that end up doing innovative things in the future that you didn't think about. Sort of the point of education. Um, so now think back to when we were doing tree sets, when we were using tree sets. Remember how in a tree set, when we had an iterator, we said that the iterator for the tree set would deliver elements in lexicographic order or the natural ordering, whatever that would be. If we stored integers in our tree set, we would get them out from lowest to greatest. If we stored strings, they'd come out alphabetic. That's because of this property. That's because the tree set is storing things in a tree structure. And when you do the iterator is proceeding in an in-order traversal like this. So there's a reason why that's happening. But you can also see that because the order in which you add things has an impact on the shape of the tree, you can't preserve the order in which someone added things to the tree, even if you can preserve the natural order. So in a tree like this, the first thing that they would have had to add was 7, and they might not have added 7 first. But you can get things out in lexicographic order regardless of the order in which they put things in. So I think that's an important thing to recognize about what we've learned and trying to draw the connection between what it is a tree set is delivering to you, why you might use a tree set, and then a hash set, in contrast, isn't using a data structure anything like this. And that's why a hash set doesn't preserve the ordering when you use an iterator that goes across it. Now, when we build this tree, when we add and remove things to it using those algorithms that we just looked at, well, it took a little bit of work to do that. And because it took a little bit of work, it can be a little less efficient than a hash set. And so if you want this natural ordering, a tree set is an efficient way to do it. But if you don't want this natural ordering, then a tree set is more than you need, more overhead than you need. And so that's why you make a choice between whether or not you want to implement a set with a hash table or with the tree set, because it depends on how you want to use it, how much computation you're willing to use in order to maintain that set. Speaking of computation, we should think a little bit about the efficiency of using these different algorithms. So the efficiency of a binary search tree operation, this is from table 2 in our textbook in chapter 17, varies a lot depending on whether your search tree is balanced or not. So down here is an example of a collection of data that's a binary search tree that's balanced. This is a binary search tree as well. It is particularly unbalanced, but it contains exactly the same data as this one does. This one only fills out the right nodes, but it's true that at any given node, everything that down the right path is higher than the node itself. It just happens to start at 0. So one thing that you notice here is that when you add things to a binary search tree, you might find yourself in kind of a bad choice. You might have made a bad decision about the way in which to add things to a binary search tree. In fact, what is the worst way to add things to a binary search tree? How is it that you would end up with this structure? Which one? So if 7 goes first, which tree do you get? The happy face one? Yeah, if you add 7 first, you're going to partition the rest of your data. What did you add first on the right one? 0. What did you add second on the right one? What did you add third? Yeah, so what's the worst way to add things to a tree set? In order. If you add things in order, either from lowest to highest or highest to lowest, you get the worst structure. what would the tree have looked like if we added things from highest to lowest? What would have been the root? Yeah, so we would have had basically the same structure, but it would have had 29 at the root, and it would have gone down the right side. Now, if you look at that, the difference between the balanced binary search tree and the unbalanced binary search tree, the unbalanced binary search tree, which is the frowny face one, that's just basically a linked list, right? There's really no difference between the structure of that and a linked list. It's just that each node happens to have a reference to the left node that's just not being used. But there's a data and there's a next, and if you think next and right are interchangeable, you've got a linked list on the right side. And so if you ask yourself, what is the efficiency of trying to find an element in a linked list? Well, it's order n. And that's because you could, in the extreme, have to visit every single element in your list in order to find it. And there are n things in your list. So an unbalanced binary search tree has the same efficiency for finding an element as a linked list does. Likewise, if you want to add an element and you're not at the position, you also have to, well, actually, it's kind of worse in a balanced binary search tree because you can't add an element at any arbitrary position. A binary search tree, if you want to add something, you can only add it in one particular position if it's unbalanced like this. Like 6.5 can only go there. So that means that in general, you have to do a linear search of all of your data, order n, in order to add something to your data. And finally, because you have to find the element as well, you have to do order n work in order to remove an element, because first you have to go down and find it, and then you can cut out the links to bypass it. Unbalanced binary search tree, order n all around. Meanwhile, in our balanced binary search tree, we have this interesting effect. Our height in our unbalanced tree is h, which is equal to the number of nodes. And we know that in a balanced tree, h is equal to the log of the number of nodes. So if we want to find an element in a balanced search tree, we don't have to search all the elements. We only have to search the height of the tree. Because at each given choice, at each given point here, we know whether the data is going to be to the left or the right because of the structure of the tree. And so because it's a search tree, if we're looking for a 0 in this tree, we don't even have to look at everything to the right side. None of that even has to be examined. We can just disregard it entirely. And so all we have to do is look at elements that are equal to the height of this tree. And the height of this tree is log base 2. And so the order of finding something in a tree, in a binary search tree, is log n. Adding an element is similar. We just have to walk down the tree until we find the place where we want to add an element, and then we decide whether we're going to put it on the left side or the right side. And at worst, what we had to do was walk down the entire height of the tree. And the height of the tree is order log, so we just have to do order log work. To remove an element, same thing. We never have to do more work than walking down the tree from the root to some leaf node. And so removing an element is order log n as well. The difference between order n and order log n can be very large. So if you remember when we took the log of 1,000,000, and I think we came up with an answer that it was something like 19.8. So compare 19.8 as just a rough relative amount of time that it takes to do something in a tree with 1,000,000 versus 1,000,000. So in something that is a tree with 1,000,000 elements, you can either do 19 units of work or you can do 1,000,000 units of work. It's a huge difference. And the difference is what? Whether you do 19 or you do 1,000,000, what's the difference between the two? Like, what is the decision, or what is the property that made one take a long time and one take a very short amount? The balance versus the unbalanced. And at this point, the only thing we know about how to keep a tree balanced and unbalanced is the order of the data that we present. But in a lot of cases, you don't know what data is going to end up being in your tree. Like, for example, if someone's going to type in the roster of your class, well, the computer doesn't know who's going to be in the class as the user is entering it in. And so if you enter in person 0 or Andrew, and then you enter Barbara, and then you enter Charlie, and then you enter Don, well, if they're doing it alphabetically, you're going to end up with a really bad tree structure. So there's no way for the software to know beforehand how to make sure there's a balanced binary tree with what we've described so far. The efficiency is, so for efficiency, it's really important to have this bushy binary tree. And binary search trees are not unique, so we're not guaranteed to have one. So that sets us up for needing a way to make sure that binary search trees stay balanced. And the way that we can make sure that a binary search tree stays balanced is by doing something called red-black trees. So the last thing that we're going to look at today is red-black trees. Since we're transitioning here for a second, let's take a little break, a little stretch break, and then we'll jump into how we manage red-black trees. Back in 5. Okay, coming back in. So the motivation here is that we love binary search trees. We love them because they're efficient and they keep our data sorted, and they have these nice properties that when we walk through them in order traversal, we get sorted data out, and we can put any kind of data we want in them as long as they conform to the comparable interface. But the one thing that happens that we don't like is when we insert things into our binary search tree that are in a poorly chosen order, and that order isn't necessarily very clear to people that are using them. What's bad about it is that we end up with a tree that's not very balanced. And so what a red-black tree does is that it is a kind of binary search tree that rebalances itself after each insertion or removal. And because of that, we never end up with a situation where we have an unbalanced binary search tree. Instead, we have a balanced binary search tree, and therefore we're guaranteed to have order, log, and efficiency, meaning that our tree filled with 1 million elements is always going to be 19 units of work rather than a million units of work, which it could be if we didn't use red-black trees and we didn't keep our tree balanced. Now, just like when we moved from binary search trees when we moved from binary trees to binary search trees, we had to add this additional restriction on the kind of data that we stored in it. When we moved from binary search trees to red-black trees, we need a little bit more information at each node in order to maintain this bushy, balanced tree property. And that additional information that we need is we need to keep track of whether or not a node is colored red or colored black. Now, these colorings are just for our purposes. It's not something that the people who are using our trees care about. And there's not something particularly special about red or black versus any other way of designating a node being class 1 or class 2. It's just historically we've talked about them as being red or black, probably because of checkers. By naming these nodes or by giving them a color, it helps us to make choices about how to adjust our tree in such a way that we keep this balanced property. So we can reduce so we know each node is colored in addition to the data that it contains, and in addition to the fact that the data that it contains is comparable. And by maintaining particular properties of our tree with respect to which nodes are red and which nodes are black, that's how we're going to make sure that we have a balanced tree. So the basic rules of our tree are that the root has to be colored black, and a red node can't have a red child. That's called the no double reds rule. And all paths from the root to a null, or through a leaf of our tree, have to have the same number of black nodes. So that's called the equal exit cost rule. And if we're able to maintain these three rules, it's sufficient to ensure that we have a balanced tree, more or less balanced. And there's a little flexibility. So here's an example of a red-black binary search tree. What we're storing in this tree are letters of the alphabet. And that's good because we can compare them and we know which one goes left and which one goes right when we are figuring out how to build our binary search tree. We have added nulls on there just so we can keep track of where our tree ends, as opposed to it being a tree we're not drawing below there. And so what we can see here is that it meets the different properties that we just described. The root node is black. Okay, we colored it black. That's fine. There's no reds that have a parent and child relationship. All red nodes are separated by a black node, and all paths through this tree go through the same number of black nodes. That might take a second to believe. Let's look at the path that goes down the far left of the tree. In that case, we start at the root. That's one black node. We follow our tree this way, and we end up exiting our tree with two blacks having passed through them. Now, if we come down this way and we had gone right, you can see that no matter which way we go, we'd also end up with two black nodes. And then even though the right side is a little bit shorter, we can't get out of this tree without going through two black nodes. The combination of these three properties are going to help us to keep our tree balanced. Here's an example of a tree that isn't a valid red-black tree. It's not valid because not all paths have the same number of black nodes. So there's one path that we could take here, starting at the root, that goes this way and then this way, that only had one black node on its path. This way had two, and so it's not equal. And so this isn't a valid binary red-black tree. That's why we have that. All right, here's an example of an invalid tree, or invalid red-black tree. And this one has violated the no two nodes being red, parent and a child. This is still okay because the root node is black, and every path that we take is 2. There's no way we can get through this tree without having 2 black nodes along the way. But there is a way we can get through this tree where we pass through 2 red nodes in succession. And so that's no good. That's a double red violation. Okay. So what do these rules do for us? Our equal cost rule is trying to prevent us from getting an unbalanced tree. Because we have to have the same number of black nodes regardless of how we traverse through our tree, what it means is that we're never going to have null references or children that are pointing to null very high in the tree. Because if we did, then we would have a path that gets out of the tree that didn't have very many black nodes. And so we're not having the equal cost rule prevents us from having short paths at the top. It also makes it so that we have to have nodes in the middle that tend to have 2 children. Because unless we have 2 children, we're going to find ourselves going left or going right and having a path that ends up having 2 blacks at the same time. The fact that we can't have double reds, but we can have double blacks, enables us to have a little bit of flexibility in the construction of our tree. As we add things to our tree, we're going to be adding them in such a way that we are adding red and black nodes so that we maintain these properties. But we don't want to have to constantly be rebuilding the tree in order to make sure that we have a balanced tree. For example, one thing that we could do in the extreme, instead of doing this red-black process, is any time that we added an element to our tree, we could take everything out of our tree, sort it in a list, find the middle element of our list, and then insert everything starting from the middle. And then we would end up with a balanced tree. That's a way that's like brute force, kind of, you know? We would completely rebuild the binary search tree every time we added something. And yes, that would give us a balanced tree. But the problem is that the work of sorting everything in order to find the middle element is n log n. And that's worse than if we just if we just went through a linked list from the beginning. So what we're trying to do is we're trying to find something that is better than working with a linked list, not as bad as sorting, but gives us the ability to get that log n time. So this no double reds rule gives us some flexibility so we don't have to rebuild everything every time. It enables some paths to be longer than others. So this isn't a perfectly balanced tree, but it's limited in how far off it could be. No paths are going to be able to be longer than twice the black height. Think about that for a second. Because you can have no double reds, and because every black, therefore, could be separated by one red node, so starting at the top with a black, you could have a red, then a black, then a red, then a black. The black height of a path can only at most have one red after it. And so you're never going to have any path that's longer than twice the black path. If you did, then there would have to be 2 reds somewhere, and that would be violating our double red rule. If you had 1 red every time you had a black node, then it would be twice as high. Try that? So just to clarify, the black height of a node is the cost of traveling on a path from a given node to null, and the cost being the number of black nodes on that path. So that's the black height of a node, and the black height of a tree is the cost of traveling specifically from the root to a null. So just subtle difference between the two, black height of a node or black height of a tree. Okay. So a tree with a black height of BH, so treat that as one variable, BH, that's going to have at least 2 to the BH minus 1 nodes. That's from our formula that we had before about calculating how many nodes are in a tree. Independently of red-black, if you had said your tree is H, then you know your tree of height is of height H. It means you're going to have 2 to the H minus 1 nodes at most. But because you're going to have more than 2 because your black height is a lower bound. You know you're going to have more than that. So you know that your black height is going to be less than or equal to the log of the number of nodes in your tree. Right? That's got to be true because the black nodes are only half of what you've got. The no double reds rule means that the total height of the tree is going to be at most the black height. So the height of the tree has got to be less than or equal to 2 times the black height, which is going to be less than or equal to 2 times the log of n plus 1. And traveling from the root to a null, you're going to be able to do that in order log n time. This is nice. These are good properties. But what's important about these properties is how we're going to maintain them when we add and remove nodes. And that's where the complexity of a red-black tree comes in. Let's start with red-black tree insertion. So when we insert elements into our red-black tree, the way we're going to do that is we're going to first insert the node just like we were inserting it to a regular binary search tree. So we'll look at the node, we'll go left or we'll go right, depending on whether the node that we want to add compares to the node that we're looking at as -1, 0, or 1. If we end up adding this node to the root because there's nothing in our tree, then the rule we're going to follow is to color it black. And that's straightforward because one of our rules is the root has to be black. Otherwise, we're going to color it red. So we're going to be adding a red node to our tree. Now that could potentially be a problem because it means that after we added this node to our tree, because all the other nodes already have a color, it's possible that we could have found ourselves adding our node as a child of another red node. And that would be a double red violation. Okay, but if the parent is black, that's the easy case. If the parent is black, then we still have a red-black tree, and so we don't have to do anything. So that's the easy case. But if the parent was red, we need to fix the double red violation. And what we can start with in this situation is we know that the grandparent has to be black. If we think about that, that's because the root node has to be black, so that we know that there's a black node in the tree. We know that we have a double red rule. We have a double red violation, and we only have one double red violation because we assume that our tree has fixed it in the past. So we have one double red violation. The node that we're adding has a parent that's red, and therefore the grandparent must be black. It's either the root or it's a black node deeper in the tree. Because of that, we can determine what the different situations are that we have and how we can resolve them. So there are 4 possible configurations given a black grandparent. In these 3 configurations, the smallest, middle, and largest values are labeled N1, N2, and N3. And then their children are labeled in sorted order, starting with N1. So let's start with the configuration over on the left side. In this case, we've just added N2. And because of the structure here, we know that N1 and N2 are both greater than N3. We know that T1, the entire tree that's to the left of N1, is going to be less than everything to the right of N1. And everything to the right of N1 is labeled T2 and T3. T2 is less than T3 because of how it hangs off of N2. And then because how T4 hangs off of N3, we know that T4 is greater than T1, T2, and T3. So we have a situation where we know that N1 comes first, N2 comes next, and N3 comes last, and the relationship between T1, T2, T3, and T4 is known. That's one topography of the tree we can have. The second case here is a second topography we could have. We could have added N1 down at the bottom here. Now this is only the case, we're only solving the case with double red. In this case, we know the ordering is this is N1, this is N2, and this is N3 in terms of less than, greater than, greater, greater than. And we know that the relationship of the trees are T1, T2, T3, and T4. Because this tree has got to be less than this tree, which has to be less than this tree, which has to be less than this tree. Okay, topography 1, topography 2, topography 3 has a situation where the grandparent is less than both the child and the grandchild, but the grandchild is N2. So it goes N1, N2, N3 in terms of ordering. And then the trees hang off as T1, T2, T3, T4 in terms of less than moving to greatest than. And then the final topography is where we have the black grandparent and the two red nodes hang off the right. So two red nodes hang off the right, two red nodes hang off the left. This one goes left, right, and this one goes right, left. So this gives us all four possible configurations of the double red, given that we have a double red to start with. All right. So what we want to do is, depending on what situation we find ourselves in on the left side, we want to rearrange our nodes and the coloring so that it matches this image over here. We're going to change the root so that whatever was N2 in these configurations is going to end up at the root. Whatever was N1 in one of these configurations will end up here, and whatever was N3 in these configurations will end up here. Because we know N1, N2, and N3 have that property because we determined it from these configurations over here, we know we still have a binary search tree. We also know that T1, T2, T3, and T4 are correctly ordered because they're hanging off the tree in the order that respects their ordering as well. The relationship between T1, T2, T3, and T4 should be maintained as well. So we need to make sure that N1 is between T1 and T2. And if we come over here, we see, yeah, in fact, N1 is between T1 and T2. N1 is between T1 and T2. N1 here is between T1 and T2. N1 here is between T1 and T2. That's okay. And then if we come over here, we need to make sure that T3 comes between T3 and N3 comes between T3 and T4. N3 comes before T3 and T4. That's good. N3 comes before T3 and T4. N3 comes before T3 and T4. And N3 comes before T3 and T4. So the relationship here is all keeping the binary search tree properties correct based on where we were in this situation previously. Now, regardless of what the coloring was in this configuration, what we're going to have the coloring end up being is red, black, and black. Now that's good because it means that given our little recursive chunk of the world here, we know that the equal paths down both sides are the same. That's an okay situation. We also know that we don't have two reds in a row anymore. That's a good situation because given this was our tree before, we certainly don't have two reds in a row from our below us. The only problem that we might have is in the process of turning this subtree's root to red, we might be hanging off some other tree below us, from above us. And we might have introduced a new double red situation one level up. Well, what we just did right here was to solve a double red situation. So we'll just recursively move up the tree and solve the double red situation one more level up. All right, when the height of the binary search tree, oh, sorry, one other point about that, is if as we bubble up to the top, we end up in a situation where N2 is now the root, we violated our property that the root of our tree has to be black. And so if that's the situation, we can just change N2 to black instead, because in that case, we're going to maintain our equal path rule. Got no problem there. And we're going to maintain our no double reds rule along the way. When the height of our binary search tree is h, so this is arguing about the efficiency of it. If the height of our binary search tree is h, then finding the place where we need to put our element is going to take at most h steps because we walk down the tree one by one. It's the same as a binary search tree. So that's going to take us log n time. Fixing the double red violations is going to take at most half of the height of the tree as we move back up two at a time, fixing it in worst case. Because we know the height of our tree is order log n, and because the worst case we have 3/2 log n, and constant doesn't change our order of efficiency, we know that the insertion process is going to be order log n efficient. So we've maintained our black-red property in insertion, and we know that that property itself didn't take more work than before. For removal of a node, before we remove any node in a black-red tree, what we want to do is first turn it red and fix any double black or double red violations, and then remove the node as if we had just a regular binary search tree. If the node's red, we just remove it. Maybe we'll end up with double blacks, but that's okay. If the node to be removed is black and has a child, well, first what we're going to do is we're going to color that child black before we remove it. So in the case here, we take this, we're going to remove this node here, and we're going to replace it with this one, and we'll color this one black to maintain the equal path constraint that this node was previously given. The difficult case is when we're going to remove a black leaf. We can't just remove a black leaf because that black leaf is impacting our equal exit cost rule. It means that if our red-black tree is good and we have a black leaf, then one of the paths is going through that leaf and having a certain cost to leave. And if we remove that node just by itself without doing any other repair, then the cost of getting down that path is going to be 1 too low. And that's a problem because we violated our constraint. So what we're going to do is we're going to turn it into a red node first, and we're going to bubble up the cost of that path violation by now keeping track of what's called a double red or a negative red or a double black. We're going to bubble up the cost of that by adding 1 to the parent and subtracting 1 from the child and trying to repair our tree so that everything has just a single black or single red value. By adding 1, we can get a double black, or by subtracting 1, we can get a negative red. So we start with 6 possible configurations of black leaf nodes that we want to remove. We either have a red parent, in which case we have the left side, or we have a black parent and we have one of the situations on the right side. This could result in a double black and a negative red. So the case on the left, that the N4, this diagram where we have the highlight around the node indicates that it's a double black. This blue node indicates it's a negative red. And so we need to fix this arrangement so that our double black credit and our negative red is repaired. So in this case, what we can do in order to fix it is we can cycle our N1, make it red, take our N2, make it black, move our N4 down here, and then move our N3 up here. So we're taking this repair process and extending it over a couple different nodes. We end up with a red here that we might have to fix as we go down again, and 3 blacks in this way. Fixing the double red violation could also fix a double black grandparent, where we have a situation where we have double reds here, and our fix ends up having 3 blacks instead. That ends up being a valid red-black tree. So if the double black reaches the root, we're just going to replace it with a single black. And that's going to preserve the cost of all paths by 1. It's going to preserve the cost of all paths being 1 and preserve the equal exit cost rule. So in the situation where we have a red and a double black here, we'll convert that to a single black here and swap those out. Situation where we have a double black here, we'll convert this one to a single black and swap those out. In this case, we have a negative red. We just move, we have a double black here. We move this, and we have to bubble the data down here and fix this side. In this case, we have a double black on the left. We move it up and then have to repair this side. In this case, we have a double black here. We move the double black up. Here we have double black here, and we move the double black. The removal is a little bit complicated, as you can see. The end result, though, is that we have a very efficient set of properties, or an efficient set of actions that we're taking. We can find an element in our tree and order log n time. So even though we've added these additional properties, this additional work of maintaining red and black nodes in our tree, we haven't added any additional work. Let's see. We've added the additional overhead of maintaining a red-black tree, but that hasn't caused us any asymptotic change in the amount of work that it's doing. So finding an element is order log n. That's the same as a binary search tree, so that's pretty easy. Adding an element isn't obviously the same, but it turns out that it is, because this red-black property is only adding at most another another h/2 amount of work to our tree. Then finally, removing an element has a similar kind of impact, although obviously removing an element takes a little bit more complexity to. Okay, questions? Okay. Well, with red-black tree efficiency, that's actually all I've got for today, or with red-black trees in general. So I think that we're about done. A little early. 11:50. Early to lunch. So just in summary today, we looked at binary search trees first, kind of cleaned up that a little bit. Looked at left-right directions for going down our tree, how we could recursively work with them. We have looked at a strategy for them, and the reason why we like red-black trees is because they maintain the balanced property, and that we like that because it's efficient. The tree gives us a lot better efficiency than the linked list does, and we want that efficiency. And then on top of that, we get the ordering on the way out. So in the quiz that's due tonight, there are going to be a few questions about red-black trees, and so you'll probably want to roll through some of the examples in the textbook. There's also a set of questions around heaps, which we didn't get to in. All right, so this is our last lecture. So we didn't open with a prayer, so maybe since it's the end of class, and we should end with a prayer. So how about that? I've got one here ready to go. So, with the end of Mayterm, except for the exam, of course, you join me in giving thanks for this. Because I don't like being on screen. All right, Father, the end of Mayterm, we thank you for all the teaching and learning that's taken place at Westmont, both in and out of the classroom, for the talents and gifts that have been shared and developed, and the challenges that have been faced, for the burdens that have been lifted and the hurts that have been healed, for the respect and care that's been given. We give thanks for the friendships that have just begun and for those that have grown. Give thanks for the faith that has been lived in our daily struggles and for the hope that has lifted our hearts on the dark days and for the love that has kept us going. We give thanks for the community that we are, and we ask you, Lord, to bless our students as they take their exams tomorrow, remotely and locally. May your Spirit inspire them with confidence and calmness. Bless our families as we take our holidays. May our time together leave us with memories to cherish. Pour out your love on us that we may return renewed and refreshed to continue our journey together. In Christ's name, amen. All right, that's it. See you at the exam. Use your extra time to work on